Hello everyone, welcome to today's webinar. The topic today are timber connections and you will see how to analyze those using RFEM. My name is Gerlinde Schubert. Today you hear me only for this short introduction and shortly at the end. And my colleague Bastian Kuhn, he will actually present the topic, and Gerhard Rehm, he will answer all your questions. The add-on module RF joints timber steel to timber is used, and we will explain the features of this module. Bastian will also show you how to design a truss of timber using the generator provided in RFEM, and the mentioned add-on module will be used to design the steel timber joints. There is a new feature upcoming in the next customer version, which Bastian will also show quickly. So this just shortly to the agenda. For those who listen the first time today, I show the control panel quickly. You can hide the control panel by using the orange arrow button, and you can change obviously the audio settings, and in the edit field at the bottom you can enter your questions, and please keep the questions short. We aim to answer them all during the webinar, and just in case there are too many questions coming in, you might get the answer after the webinar via email. So that's already all from my side today, and I now hand over to Bastian Kuhn. Enjoy the webinar, and I hope that it will be very informative.
Okay, thanks Gerlinde for the introduction. As announced, I'm going to create a truss using our model generator. Probably I'm defining a position called truss under the project name webinar. For this specific truss, it is enough to have a 2D model, as the modeling itself later on is much easier and faster then. So I choose a 2D system in X and Z orientation. I'm not going to do the automatic combination of load cases, as this is also demonstrated in other webinars and should not be the task of it, but for sure it is possible to do some combinations here according to, for example, Eurocode and other countries. Okay, but we'll do none. Say OK and create the model. I'm now in the RFEM screen and gonna generate the model under Tools, Generate Model 2D Truss. And I would like to have a number of bays, for example 8, and the total length of 28 meters and the height of my truss of 5 meters. The profiles of the structure for the upper chord, I'm going to define a rectangle width 160 millimeters and height of 320. There are a lot of other possible cross-sections for timber structures, for example, this joist hangers or T-beams, but for this truss I think it's enough to do it with rectangle profiles. As material, I'm going to use glulam material out from the database for the British standard. Where is it? Right on top. And I'm going to choose GL24 homogeneous. Okay. And now it's in. Then for the lower chord, I'm also going to define a rectangle, but it will be 160 and a height of 300 millimeter, but from the same material GL24 H, and the diagonals I can use a little bit smaller. I choose a rectangle 12 by 12 centimeter, and of course it is enough for this to use softwood and no glulam anymore. Can also filter that out and go to British Standard C24 material. Okay, and I'm gonna choose the same for the verticals. No. You see here that I'm also able to define which kind of member type I want to have. There are all the members that are possible in our program available. For upper and lower chord, it is correct to choose the member type beam, and for the diagonals and verticals, truss is sufficient. The orientation of the diagonals I'm going to choose in a way that I will have tension in all the bracings. So that's why I orient them in this direction. And now the model is already generated, and I can continue the modeling. I'm going to delete the set of members as I don't need it for this demonstration. Now where the beams come together, so on the eave end on this side and on this side, and also on the ridge on this and this point, I need to define a moment hinge because they are fixed to each other, and that's not possible for a timber connection. So for the member start, I choose a moment release around Y, and here also for the member end, and of course on the right side I'll do the same also for the member end. Okay, let me flip that out. Okay, so now the truss is already modeled, and I can take care of the loading. As first load case, I choose permanent load situation and activate the self-weight. And I'm going to define a member load in global Z direction, but related to the true member length of 1.2 kilonewton per meter. Then the next load case is for snow, and there I'm also going to define a member load, but now related to the projected member length with 2 kilonewton per meter. As I told when I started the webinar, I'm not going to do an automatic load combination, but I do a user-defined combination with new load combination, and I choose load case 1 and load case 2. Directly the right safety factors are assigned, and I'm defining a linear static analysis. Okay, the supports I missed. So on the left side, no moving in X and Z direction. Y is prohibited directly from the start. And in X direction on the right side, I make it movable. Now I can have a look at the inner forces, if it's plausible and if it's correct. And looks actually pretty good. Just have a look at the normal forces. So that's all alright. I have pressure on top and tension on bottom, and all the diagonals are under tension just like I wanted it. But now I also realized that this post in the middle is pretty useless. As you see here, it gets hardly any loading, and it also gives nearly no stiffness to the structure. So if we look here, 36 millimeters deformation, and if I delete it, I assume that it's going to be pretty much similar, and it is actually the same. So it's absolutely useless to produce this and so I get rid of it now. And then I'm going to design the connections. Therefore, I start the module called RF joints. You can start it either in the navigator or through the drop-down box under connections joints. The module joints in global consists of several modules that are integrated in this. On the top you see already that you have two choices of material. So if you choose material steel, you can get there the module column base, pinned joints, tower, and DSTV. So each of them is a separate module that is completely based on its own. And if you choose timber, for now, it is possible to have there right now the group or the module steel to timber connections. And under this module, we are currently implementing the definition of bolts, nails, and screws. Those are about to come pretty soon. Right now it's possible to define their dowels sliced in with steel plates or outer plates. I'm going to demonstrate that later on. For this category, we have now 3 types of joints. The first type will be main member only. It's not just for one member. You can have up to 50 or more members on this joint type. So that's all possible. And it's pretty smart to do it if you have a very sophisticated structure, or if you have just little pieces of inner beams in beside, or if you have a cantilever attached to a concrete wall. That's actually where you would choose this connection type. For this truss that we're doing now, we're not going to use it, but just to give you an estimation what it's created for. So the second joint type we're actually going to need, this is with continuous member. So, and the continuous member is, for example, the upper chord or the bottom chord, wherever it attaches to the braces in the structure. And then the third one is without continuous member. This is actually for the E-fence on the left or on the right, or for the ridge where you have no continuous member. So that's the difference. Then the boxes down here below, cutting main member and cutting connected members, are, as the name says, defining how your beams are cutted. I'm going to demonstrate you right in the design process what it actually does and where you need it for. So I don't want to say too much about it now. It is possible to calculate according to the Eurocode with several national annexes. For now we're using British Standard. Each safety factor that you can find in this national annex, it's just like in all or in the most of our other modules, is possible to be changed by the user. So you can say, okay, for the timber I want another safety factor, and for the connection and for the steel plates I want it different. You could also, for the dowels, make a user-defined definition of the distance between the dowels. So that's all possible. Then there are further additional settings. One of it is to design the truss according to the system VST from the company SFS. If you select that, the steel plate material, the dowel material, and also the diameter of the dowels is grayed out, and you're not able to change it anymore because it's all predefined according to the approval from the company SFS. So that's all possible. And if you don't use it, for sure it's possible to say, okay, for steel plate material I want any kind of steel that you would like to have here. For now we're using S235, but everything else is possible. The next check is for minimum spacing between dowels. That is a little bit hard to understand probably, but if you remember the introduction that Gerland gave, maybe I can just flip it back to you. Hold on. There she showed us this little picture from a frame corner, and there you see you have the inner and the outer radius. And if you remember that, and we get back to the module, the limit between inner and outer radius of such a connection is not really regulated in any standard, but it for sure makes sense to check it somehow. And so you have the chance to do this here. This is what this check is for. And because it is not regulated in any standard, it is possible to define this distance that is checked in the module here by yourself. So you can do whatever you want there. The next check is for contact of members according to the deformation. it actually makes sense when you have, let's say, a high pressure coming on this post here, and it assigns the pressure to the bottom girder. And now what should we do with this? It will influence your inner forces, but in the program itself it is connected, so this is actually, it checks it, and if the deformation there gets higher, or if you get pressure there in this area, it will give you an alert. That's actually what it does. And the last check is, so that's pretty easy, it's design of main member double group from sum of connected forces. So for example, if you look for the eve end, and if we look for the inner forces one more time, moments is maybe not so interesting, but so shall it use the resulting force, or shall it use the force that I have here on each member end? That's actually what the check does. So you have these two ways there. Okay, so that is the first mask, and now we're going to get to nodes and members. You can either import your definition type from the structural model, or you can define it manually. If you define it manually, you are absolutely free in everything that you do here in the module. You can change your angle, how the members are oriented. You can then later on also define any force on the structure that you want. It's one of the big advantages, so you can like manipulate it in the way that you would like to have it. And the other choice, as I said, is import from structural model. That's actually what we are going to do here. And we're going to start with the eve end. So I choose node 1, and because it's a symmetric truss, it's the same on left and right side, I can choose the second node as well. Then the program already found out, okay, I can define there some senseful geometry, and ask me, shall I do that? And I say, okay, yes, do it. Now I can have a look what it did there. My connected member is now on top, and my main member is on bottom. I'm going to show you in the next two masks what it actually has to do with this. Then I'm ready with the definition type, and I go to the mask loads. So I say, okay, I want to design the loads for combination 1. Load duration and service class is automatically assigned, but I can change it here as well. You could also change your service class. Let's say, for example, if you have an overhang on this side, you would choose for the overhang a different service class than for the beams that are in the field. That you could do here in this mask, but for now we don't have any overhang, we are fine with that. And go to the most interesting mask of the module, the geometry. So you see already, this is not what anybody will really produce in practice. So it's not really possible to make something like that. Therefore we go to general data and change the cutting type. And if we change it to the third box of the cutting type, you can see that it cuts it right in the end where the bottom and the top girder align. And if you choose the middle type, you can see that it's like draw to the end. Now, if I come to the priority that I told you before in the masked nodes and members, it's not so economic to have the top girder aligning to the bottom girder, because it gives pressure to the bottom girder, and pressure rectangular to the grain is not so good with timber materials. Therefore I want to change it and let the top girder go through, and I could easily do that by defining this as main member and this as connected member. Now the program also found out, okay, you changed the first node, shall I do that for the right side as well? Yes, I do that. And if you look back to the module now, you see that's how I wanted it. The pressure from the top girder goes now directly into the support, which is in most cases more economical. You can define up to 5 steel plates, whether sensible or not. You can also define side plates. and assign them there. But for the first start of the iterative process, I'm going to start with one steel plate and of course no side plate. Thickness, I'm going to choose 12 millimeters, and the distance from double plate to edge, I'm going to define 24 millimeters. Now the steel plate is defined, and I can define the connection on each member. And I start with main member. The geometry of the connection is possible to design as rectangle or as circle, but a circle for this connection makes not so much sense. That's why we are always going to stay with rectangle here. And a diameter, I choose the same as the steel plate, 12 millimeters. You can define a plug, even if you have some visible things you want to regard, if you don't want to look at the holes, or if you have some verifications for fire resistance you need to do, it's possible to do that. And the dowel then itself is automatically shortened. So you see it has been 160 millimeters and now is shortened on both sides to 120. Okay, the number of dowels in X directions, I will choose 8, and in Y direction I leave it by 4. I could also have it with staggered rows. That's much more economic because it you don't have so many dowels lying near to each other, and it is more advantage for the calculation of the N effective of the dowels. For the first iteration, I'm going to leave the possibility of group placement with minimum edge distance. It's also possible to define minimum dowel spacing, but yeah, for sure when you want to design a truss, it's much stiffer and more load bearing capacity if you are always working with minimum edge distance. And it's also possible to choose user defined. Okay, and now we use edge distance. The orientation is also possible basic, which goes along with the local orientation of the beam you are designing the connection on. You can rotate it by any angle. You can slant it according to the slope of the beam, and you can as well also have it user defined. But here we go on with the local orientation. If your dowel group is overloaded, and it is because of the overloading of each dowel, you can also calculate with N effective equals N. So you're not going to lower it, and therefore you have to define screws that you can also do either automatic or manually. And you define it manually, you can define any capacity of the screw that you want to drill or to screw into the beam, yeah, manually. But as I said, for first iterative process, we just want to look what the program does and where we're going to end. Then we go to the connected member. So here's something special. I already regarded when we looked at the structure or at the inner forces that there's a pretty high tension on this bottom chord. So that's something I should remember during the design process, and therefore it makes absolutely more sense to have in X orientation more dowels or as much possible dowels as are possible. So I'm going to define 10 and just 2 in the Z direction. I could use staggered rows as well, just to demonstrate you something there later on. And here, as I already knew, okay, there's probably going to much force, and it makes really sense to have at least a bigger distance in A1 direction. So I define 12 centimeters, and in A2, the lower will not be so high, 16 centimeters. And then also, you see that here, this distance here is pretty low, so it really makes sense to get the whole connection more to the inner side of the field, and that I can also define by flipping the whole group or the center of the whole group, let's say 16 centimeters into X direction. The staggered rows, I wanted to explain you also something, how this algorithm works. If you look for this detail box here, it is possible to define any kind of diameter of the dowels different. Now I defined every dowel 12 millimeter diameter, but if you, for example, have some bolts that should be 20 millimeters, let's say, okay, on this side and at this point it makes really sense to have a bolt that fixes your structure, it is also possible. And this changes is also regarded for the stiffness of the structure, and it will be also regarded for the deformation of the dowel. So, and you see how the algorithm staggered rows works. It actually just deletes one after the other. So this is how it works. Okay, this picture that you have here, or this geometry picture of your connection, you can also save and assign to any other structure. But I'm going to show that on another connection in the next step. Okay, so definition of the geometry is done, and I can calculate it. So and now you see, okay, I got some pretty high overloading. I got the steel plate overloaded by bending and shear and axial forces, and I also got an overloading of each dowel, and my minimal distance is also not correct. You see A for tension direction, let's overload, yeah, okay, that's obvious, as you see here, that's pretty much on the end, and you have probably some tension there. If we look for the forces, here it's possible to see the reaction forces on the beam. Maybe it's more interesting if we look, or more obvious if we look for the bottom. Alright, you see here the reaction forces on each dowel, how it is assigned to the group. In this verification 6010 you have every force on every dowel separately demonstrated, and also the loading of each dowel you see separate. So if you look for first dowel, that's actually this one here, and so you see it bears a load of 17.8 kilonewton, and it's deformed 0.9 millimeter, and the load to grain angle is 3, and so on. So all these informations you have here. But let's get back to the main member where we have the most problems. Also, what other critical verifications do we have? I think that's pretty much it. Also, this one is something also, yeah, pretty high to critical. This is the tearing apart of this member due to the moment rotation. So these are all things I need to regard now when I improve the design of the connection. Okay, so I go to main member and say I make user defined, and the same as I said for the bottom girder counts here as well. In A1 direction it's always very economic to have a very big distance there, so I choose that as well, 12 centimeter, and in A2 just to have a round value 75. And as I had problems with A42, I can like also move the whole structure into the X direction, let's say about 14 centimeters. And as I also had a problem with the tearing on this side, with 98% loading, I'm gonna choose a little eccentricity just to have it more lifted to the up here, and then switch to connected member, have a short look to the demonstration. So okay, that's pretty good. I just want to see where it ends. Okay, so we still have an overloading here of 40%, but everything else seems to be fine. Okay, and oh no, it's that should be rectangle actually, and this one as well. So for now, what else can I do? Maybe if I just have overloading in the dowels, which is the case right now, choose for this situation a higher diameter. So then I get some problem with the limit distance. Okay, and where do I have it? In A4T direction. Okay, better to go with 12 millimeter, I think. And this, and one last chance, what we could do to improve it is assign 2 numbers of steel plates. That's probably something where you get also the load much more homogeneous into your structure. And I'm not going to make it uniform, but I make the inner piece a little bit thicker, just to have, as I said, a better homogeneous load into the structure, and then design it again. And now, hooray, it works. So critical verification is still the tearing apart of the structure, but verification is fulfilled. And timber cross-section verification for tension. To that I can also lose a few words. The check of details I did not explain so far, and that has a special reason. There are 3 choices to define your design value settings. The one that we do here is doing the capacity of FVRK, of the whole group of the connection. Then you can also calculate it with the embedment strength, FHK, and the yield moment. That has the advantage that you can choose the safety factor for the embedment strength in the wood with mostly 1.25 or 1.3. It depends a little bit on the national annex in the Eurocode. And the safety factor for the yield moment you can use for steel, which is in most cases 1 or 1.1. Depends also a little bit on the annex. The third check is something especially for the German annex. It is with the required minimal thickness of the structure, and it's not relevant for Eurocode. And the options you can define if you want to reduce the slip curve that's exported later on to the program. I'm going to say something to that as well when we have done the design process, by either KU or by gamma M. And these other checks are just with reducing or increasing the strength for stress analysis of the timber. I'm not going to say too much about them right now, but what I was up to is the reduction of timber tensile strength. This is also something just evaluated in the National Annex of Germany. And if you don't want to do that, you can also check that off, or you can either say, I want another reduction coefficient. So and if you remember, we have 96% now, and if you switch it off, it should be pretty good. So you see it's around 40, so that fits pretty good to the 60 or to the factor that we have assigned there. Okay, good enough for that. And now we're going to define the ridge and define a new case for that. We call it ridge. Say okay. The other things of the first mask should be clear, but now we would also need without continuous member and define the node. Actually, I don't want. And say, okay, node 6. I also set it to default. Important is to have a look now if your main member is the upper chord, which it is what it is not right now. And if you look to geometry, the main member cuts your system. So, and that's like a pretty nonsense structure. So it's important to see, okay, my upper chord in this case is the main member. And then it should be good. One other thing is the priority of the member. I can also demonstrate you. You see that's actually just like I wanted it. And if you change this priority of the attached upper chord to, let's say, 3, and you see then it's also still nonsense, because now this is the second cutting of the connection, and it's also not sensible, and therefore always choose, for such a situation on the ridge, choose main member, upper chord, and the first priority to the next upper chord. Okay, loads the same, and geometry. I'm going to also start with number of steel plates 1. I can define 24 millimeters distance to the edge. That I did not explain. It's possible to define another width of the slot different to the width of the steel plate, but it's just for assembling needs on the job site, so not for the design process. I choose 12 millimeter diameter, and what else do I do? In X direction 6 dowels on the main member and 3 in Z direction. I can directly go with user defined distance, let's say, okay, 6 centimeter in X direction and 12 in Y. The rest I can leave. Now it is possible to save this group, which is very sensible because I have to define the same on the right side of this beam. So I save it and say, what do I call it? Ridge upper chord. Okay, and then I go to the next connected member, go to the database and have it there, say okay, and it's all in. Diameter and everything else. Then the bracings. I can also define 12 millimeter dowels just to have it similar on both. 6 dowels in X direction. As you see, this brace is pretty slim. Maybe it would have made sense to make it a little bit thicker, at least in its Z orientation. But now we go with that. We try to go with that. And in Z direction, choose 1. And then as a distance, we choose also user defined and 8 centimeters in X, and there's nothing to do with A2, and A3T we leave actually like it's proposed by the program. Now you've seen that for these braces it is possible to define some member eccentricities. When I've done the design process of the truss, I'm going to show you what this is all about. Now this connected member I save as well. Say con whatever 1. No, it's not 1, it's 2. Con 2. And then go to the third connected member, go to the database, choose it, say okay, it's also in there, calculate it, and the verification is successful. Okay, main loading is for the dowel as well. The design for the timber cross-section is not really relevant here, but I forgot to say that. So the module does all the timber cross-section verifications necessary in the connection area with the reducing of the cross-section values according to the slices of the steel plate and also according to the holes drilled for the dowels. Okay, what else? Critical verification. Maybe if we look here, yeah, you see that's maybe something interesting. We have now a loading of 43%, but if you check on the reduction of the tensile strength, yeah, we already know now it should probably be near to overloading or overloaded, and you see it's overloaded now 9%. So that's what I said when I did the modeling. It's a very long base, and I don't know, 6 or 7 meters or something like that. And with 12 by 12, that's really pretty slim. That's something you would probably change when you do it, the design process for it. Okay, but now we go with it. Check off the tension reduction, and then it's fine. Then we go with the next case, and that will be the continuous members on the upper chord. I'm not going to do the bottom chord today because I think it can be pretty annoying for you to see me doing this 3 times the same thing. So I'm just going to define this, and this bottom chords I leave as they are. Now I would need a continuous member because it is now the upper chord, and first time I do it with node 4 and the symmetric one is 8 in this case. Define it as default, that's all the same. Geometry, that's also the same, but here I go with 24 millimeters again, and here on main member 12 millimeter diameter, and in X direction 4, in Z direction 1. So if you look for it now, something like that, but I can already see that on here, if we make the cut with, I don't know, some CNC machine, it would be more user-friendly for the carpenter who assembles the joint if you put that pretty high to the edge of the end, because then the cut must not be so deep. So that's something I can already influence here. Once again, A1 should be pretty big, so let's say 10 centimeters. A2 is not relevant, AX also not, but the eccentricity into the local Z orientation, that's something I should move, and I can try to move it 2 centimeters out, and you see 2 centimeters out, that's already something. If you look, we have a truss of, or a beam of 32 centimeters, and the cut here is 16, which is pretty high, and a cut of 14, that is maybe easier to do, 14 centimeters. Okay, this connection I can also save. When we say corner 4, or let's say point 4, and we call it upper chord. Okay, then connected member 1. We go also 12 diameter, 4 dowels is okay, but 1 should be enough, as there's also a pretty slim brace or pretty slim post. And the distance we make user defined with 6 centimeters, and 84 we leave. And the next brace, it's this one, 12 millimeter diameter. Let's try 3 in X direction, and user defined, oh no, not edge, here, user defined 8 centimeters, and A3T, yeah, you see, that's the same actually what I showed you when I looked for the event. This is now a very low distance here for A4. So I also want to have that more to the inside of the beam, and so I try to go with 14 centimeters here. So now it's much better. Okay, then calculate it, and that's also okay. Let's look for critical verification. Okay, the steel plate is pretty high loaded, but the steel plate shown here is just to the edges of the distance. In reality, if we look also for the graphic, that's what you have here. Let's say get main out, connected, just look for the steel plate. In reality, the steel plate would be much bigger, so it's not really that critical as it's assumed to be here. One thing I also forgot is the geometry mask in the results. Here you have all the basic parameters of each connection. So if we look for the main member, you get the geometry informations, steel informations with cross section and so on. You get the chamfer angle for load to grain. You get the slip modulus for ultimate limit state verification and for serviceability limit state verification. The polar moment, all those things what we later on use for the stiffness calculation. All right, and now the last nodes that need to be verified is the nodes 5 and 7. I'm going to show you that I'm right. So that's also continuous member. Go here, nodes member, and then select them. Know that we had, so this node 5 and node 7. Okay. Assign it. Yeah, that's the same. And geometry is this all the same like we had before. And here for the main member we can use our database because it's pretty much the same. Say okay, assign it, then it's all in there. Yeah, maybe try to use one dowel less here with 3, but the rest we can all leave like it is. Now I forgot to do it for the other ones, so I quickly gonna repeat just the input. If I've saved it to the database, it would have been easier now, but it's not that much work. Minimum edge, user defined, and 9 centimeters, and this will all leave, and then the connected also 12 and 5, 1, and this user defined 6 centimeter, and the rest will leave. Okay. So that's all good. The geometry mask I showed you, we just now looked for the design summary as this is the most relevant mask where you have all verifications that you need. Code cases or combinations defined, it also makes sense to have a look on the mask 3.2, but as we have just one combination done here, it's just a global overview of it. You have the verification for each node. It's essential to look for that also when you have unsymmetric loading. You know, now we have symmetric loading. The loading on left and right side of this symmetric truss is the same, but it could be different. And the graphic mask I showed you as well. Here you can also select the dimensions of the structure. You could also print that directly to the protocol. So that's all possible there. Now if you look to the global program, RFEM, all the things I showed you right now are also possible in the program RSTAB. So there's no differences. You can have a rendering of your connection directly in the program RFEM. You can show them all in one. So you see, I did the design for this, 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 and this. And this we did leave out. But now the design process of the truss is done. And I can show you something that is not yet in the customer version, but it is under development, and it will be pretty soon be exported to the customer version, and then you can use it as well. It is the automatic export of eccentricities and stiffness that you have assigned here. This automatic export of the stiffness is just possible in the program RFEM. It's not possible in the program RSTAB, but the eccentricities of the braces, that is possible in RSTAB and RFEM. So that's one difference. But everything else I show you here is possible in both programs, RSTAB and RFEM. Okay, to do that, to export the stiffness calculated by the module, I have to change something in my modeling. What we did now when we started the design or the modeling of the structure, we defined here moment hinges and also truss beams that have also a moment hinge. Now if the module designs the stiffness, we have to make it rigid before, otherwise it won't work. And therefore we are going to delete the member hinges and also the braces we're going to make to a beam, not a truss anymore. So now there's moment rotation. Those posts on the far end I'm going to leave because I did not define any connection there. Also all beams and all posts and braces that are attached to the bottom chord need a moment hinge as well. So for member start, all this, no it is not, and this, I can do a moment hinge. Okay, okay, and I missed this, and define there also a moment hinge. Okay, and all other stiffnesses are exported from the program, from the module joints, timber, steel to timber, and you see now, okay, there's moment, we have a moment transmission from one beam to the other, what we did not have before. Then we go back to the module, and now we're going to change some parts of the definition. If we look for this connected member number 1, yeah, 1 in this case, it's obvious that it is round about 14 or 15 centimeter eccentric assigned to this upper chord, so we can define it in global direction, let's say 14 centimeters, just to give you an estimation what it does. We also do the same for the connection of nodes 5 and 7. Actually do it the same amount. Oh no, not this. Connected member. You see, for connected member number 2 it would be much harder to do, as you need to align it with the physical system of the model. Okay, then it's done. And now if we go back for details, that's also something I grew out when I showed you the timber details. Here in general you have the possibility to generate member eccentricities to, once again, either RSTAB or RFEM. That's possible in both modules. And only in RFEM it's possible to generate the connection model to the structure. So, okay, this means I have to delete the results, that's clear. And now if you calculate the first case with the event, then you see pretty high overloading, but I just want to demonstrate you what it did. It exported the slip curve and also the eccentricity of the gravity point of the connection and the distance to the gravity point of this connection out to RFEM, calculated the inner forces and did the design process. I'm going to show you also in the module, in the program RFEM. So you see it makes a nodal release that has actually no connection during the calculation here and also on this point, and then it makes a fictive member that is connected from the gravity point of the upper chord and from the bottom chord, and this member contains the stiffness that we have assigned in the result mass that I just showed you there. So that's one terrific part of it. And then here on this post you can also see the eccentricity that we defined there is also exported from the module joints out to RFEM. So you see here generated from RF joints. Now if we calculate the whole position and look how the loading goes up, we assume that the loading of the connection goes up, because if you look for the resulting force for the moments and also for the shear force, you see that in the field the moment is lower, so which means I have less load bearing of the beams, but I have more load assigned to the connection. So you see we have here a high peak of moment that's actually assigned here, and you have for sure also a high shear force, because you have just the little cantilever from this support to this support is also a pretty high jump that you have. And now we look for the results of the loading. So when you see, okay, that's now pretty much overloaded. The only thing that's still possible to design like this right now is the ridge. That's still possible. But eave end and also the braces on the continuous beam are not possible. Just have a short look. So I have a timber overloading in this specific area here. Yeah, I have. That was already a pretty close problem before. This tearing apart of the upper chord, and so here I have an overloading of the steel plate. Okay, that can be maybe improved by using 2 steel plates. But what I was up to show you was that you have like completely different forces right now due to the stiffness. Okay, from my side, this is all, and I'm gonna actually get the mic back to Gerland. Thank you.
Many thanks, Bastian. This was very informative. And I want to use this chance just to finish up. I want to advertise the next webinar. Today we were just talking about timber, and the next webinar will be about steel connections. So I want to show you, like you can't see my screen right now. Here you go. Hold on for a wee second. Yeah, now you see my screen. And I just want to show you the next webinar. So when you go onto our website, it's www.dlubal.com, and go on the left-hand side, you have a few choices here. And when you go onto webinars, you get a huge list. And there's the upcoming webinars first, and then the previous webinars down here. So the next one is about analyzing steel joints by using RF joints to the same add-on module, but Bastian explained it. It's split it off in timber and steel. So the next time we are talking about the steel part. And when you're generally interested in timber constructions, you could have a look down to our previous webinars. It's quite far at the bottom because we did them already in the year 2012. So there's one from December 2012. It's analyzing of timber structures with RSTAB and timber professional. So this might be of interest to you. And there's another one, analysis of cross-laminated timber. And the last one I want to emphasize is this one down here, analyzes timber structures. So this just for your information. And I want to thank you for your attention. And I hope you found it useful as well. And I hope to hear you soon again. Bye-bye.